paper. I had asked 4 questions. So I will go one by one and basically discuss the solution. So the first question was related to propagation of uncertainty. The question says that air flow rate of 17 meter cube per hour to a pipe of 60 millimeter internal diameter at 20 degrees centigrade is measured using a square edge orifice of beta 0.4. A pressure drop observed is 157.85 Newton per meter square with plus minus 0.4% uncertainty. So this is the uncertainty in the measured pressure drop, that is 0.4 plus minus 0.4%. If the area of orifice is maintained within 0.2%, that means the uncertainty in the area of the orifice is 0.2%. When we say percentage, that means the uncertainty value divided by the original value or the nominal value into 100 gives you the percentage. Okay. So it says that if the area of orifice is maintained within 0.2%, estimate the design stage uncertainty in the flow rate. Estimate the design stage uncertainty in the flow rate. Assume uncertainties of the coefficient of discharge CD and density rho are both plus minus 0.5%. You are asked to estimate the total error in the measurement for CD equal to 0.63. Here the pressure P is 0.97 bar absolute and R is 287 joule per kg Kelvin. So this is the formula that is given. You are asked to find the total error in the measurement of the Q. Okay. So how do we solve it? Okay, let me show you the fundamentals, what we studied in the class. This is the one, yeah. So this is what we had discussed when we discussed theory. We said that if R is a function of many different variables, right? And the uncertainty in R is going to be a function of uncertainties in each of these variables, right? And this uncertainty in R we find by taking end of R with respect to each of these parameters evaluated at the mean value into the corresponding uncertainty of that ith variable whole square, and you sum it off for all these variables and take half. This is the root sum square approach. This is something that we had studied in theory, right? Now in this case, R is basically Q, okay? And R is Q, and each of these variables x1, x2, x3 are basically CD, A, N, delta P, and rho. Okay, these are like x1, x2, x3, x4, 4 variables, right? So we do the same thing basically. So you have theta I is basically dou R over dou xi at x mean into the uncertainty individual variable square and sum it and take square root. Same thing we are going to do here. So this is the solution I have. So I have Q is equal to CD into A square root of 2 into delta P over rho. So first, if I want to know the delta Q, it will be del Q over del CD into delta CD whole square plus del Q over del A delta A whole square plus del Q over del delta P into del delta P whole square plus del Q over del rho into delta rho whole square root. And so this derivatives dou Q over dou CD. So if you take derivative of dou Q over dou CD, it will be A into this term under the square root. So which is nothing but Q over CD. Similarly, if you take dou Q over dou A, it will be CD into this term. So which is nothing but Q over A. Okay. Similarly, if you take dou Q over dou delta P, it will be Q divided by 2 delta P. If you take dou Q over dou rho, then that would be Q over 2 rho, right? Because square root is there, so half will come, and that is why you will get Q over 2 delta P here, Q over 2 rho here. So as per the formula, the uncertainty in Q divided by Q will be equal to the uncertainty in CD. So basically, the uncertainty in Q will be uncertainty in CD into dou Q over dou CD. Dou Q over dou CD is Q over CD whole square. Now each of these terms you will have Q square, Q square, Q square, and Q square. So that there is a square root. So that Q in the numerator has come here. Okay, so this is basically uncertainty in Q divided by Q that has come from there. Now the remaining term is basically uncertainty in CD into dou Q over dou CD, that is 1 over CD. So here, whole square. Okay. And same thing for the area term, the uncertainty area into dou Q over dou A whole square. Okay, so 1 over A whole square because Q has gone there. Similarly, for this third term, it will be this term, uncertainty in density into 1 over 2 rho whole square. Uncertainty in delta P divided by 2 delta P whole square, then whole square. So now, so this is the formula. This is same as what we have seen here. Okay, exactly same as what we have studied in theory. Now, what is the individual uncertainties? So as per the question, you can see that uncertainty in the CD and rho are both 0.5%. So that means delta CD over CD is basically 0.005. Similarly, delta A over A is 0.002. Delta of delta P divided by delta P is 0.004. And delta rho over rho is 0.005. So all these uncertainty in CD, area, pressure, density are given in the question. So this is the CD, this is the area uncertainty, this is the delta P uncertainty, and this is the rho uncertainty. So all these are given in the question. So you just note it down here. Then the only other thing that you do not know here is, you know, CD, area, delta P, you don't know density. So from the question, you have pressure given, R given, temperature given. So using this as air to be ideal gas, you can actually get the density. So your density is P over T. So pressure is 97.97 bar. So which is here, divided by R is 287, T is 293 Kelvin. So this comes out to be 1.13 kg per meter cube. Okay. So now you have all the quantities. So if you just substitute here, you can actually show that your uncertainty in the Q is basically 0.006 into Q. Okay. Now, you do not know what is the nominal flow rate. So nominal flow rate you can find out using the formula that is given, which is CD into A into square root of 2 delta P over rho. CD is given 0.63, right? The distress coefficient is given 0.63. Area is given, right? It says some 6 millimeter, 60 millimeter ID. So that is given. And then 0.06 square, right? And you have delta P also given 157.87 Pascal, and rho you have density you have found 1.13 kg per meter cube. So if you do the calculation, this you will get 0.03 meter cube per second. So that means your uncertainty Q will be 0.006 into 0.03 meter cube per second, which can be, this is 0.006 into 0.03 meter cube per second, which can also be written as, you can write as liter per minute. So 1 meter cube is 1000 liters, so you multiply by 1000. And when you say go from second to minutes, you have to multiply 60. So if you do the calculation, this will come out to be 10.8 liter per minute. So that means your uncertainty in the flow rate will be 10.8 liter per minute. So in this case, this is the flow rate of air, meter cube per hour. So it will have an uncertainty of nearly 8 meter cube per minute. Okay, this is what, sorry, 10.8 liter per minute will be the uncertainty. So this is the first question. Okay. So this is nothing different than what we studied in theory. Just you have to take the derivatives correctly and put the, the uncertainty values that are given correctly, and you will get the correct answer. The second question is about...
Sir, just sorry to interrupt, sir. Sorry, I missed due to network issue. So, like, what is the reason for like the edge orifice beta?
Oh, okay. So this is not, used here. Okay, this is this parameter that is given is not used in this question.
Okay. Okay, sure. Thank you.
Sir, just one doubt.
Yes.
So in our calculation, we used directly the percentage error, right? So instead of that, can we calculate the error itself from CD value? For example, CD is plus or minus 0.5%. So can we calculate the error value directly and then solve?
You see, any way you do, like for example here, if you have the CD value, you multiply and you can calculate. So in any way you do, finally the answer should match.
Understood. So a CD value we can take as 0.63 itself, right?
Yeah.
From the question.
Yeah.
Okay.
Yeah.
Okay.
Okay. So if your calculations are correct, it will yield the same result. Okay, so now I move on to the second question, which is about finding a appropriate curve fit. Okay, so the question is: a velocity probe provides a voltage output that is related to the velocity u. Okay, like we talked about, the hot wire anemometer, where the output voltage is related to velocity. And it is in the form that the output voltage is A plus B u to the power m. Okay. So this is the relationship between the output voltage E and the velocity u. A and B are constant, m is also a constant. A calibration is performed and the data are recorded below. So this is the voltage, this is the corresponding output, this is the velocity and this is the corresponding output voltage. So when the fluid is at rest, you get an output of 3.19, and as you have higher and higher velocity, the output voltage is increasing. The question is, you find an appropriate fit. Okay, find an appropriate curve fit. Using this data, you have to find basically A, B, and M. Okay, and find the standard error of fit and goodness of the fit. Assume 95% confidence interval. Okay. So, how do you do this? First, you have to get a fit. Now, to get a fit, normally we have studied, fit for linear equations. Okay. I think we did for quadratic also, but linear equations we have studied in detail. But this is not a linear equation. This is a non-linear equation because this exponent is there, u to the power m. So how do we approach this? The solution. Okay, I have to show you the solution. Just give me a second. I have not. Just give me a second. I hope you are able to see my screen.
Sir, visible.
So this is the equation that we are talking about. Okay, so this is the equation that we are talking about. And So E equal to A plus B into U to the power M. This is a nonlinear equation, right? So we do not know for this equation how the constants can be determined. But you can linearize this equation. When you have some kind of exponent, you know that if you take logarithm, then you can linearize this equation. So you can write E minus A is B into U to the power M. Now if you take logarithm on both sides, so it will be log E minus A will be log B into U to the power M, that will be log B plus log U to the power M, and log U to the power M will be M log U, right? You all know that log x to the power n is n log x, right? So now this equation that you see here is basically a linear equation. So this is in the form of y equal to mx plus c, or y equal to, in this case, this you write as b, and this is as m, and this as x. This is a linear equation. And from the table, if you look at this table, it is given that at u equal to 0, E is 3.19 volt. So you can see that when U equal to 0, E is 3.19 volt. So you can see from here, when U is 0, this term is 0. Okay. And E is 3.19 volt. So that means A, this constant A, must be 3.19 volt. Okay. This is from the data itself. Now, U is 0, right? And when U is 0, E minus A is 0. So log of 0 is not defined. So that means you don't have any information here. Also, when U is 0, log of 0 is not defined. So you don't have any other information. And here, when yeah, so when your E is sorry, U is 0, your curve is basically A, which is 3.19, which is same as the experimentally obtained value, 3.19. So basically the difference between the data and the curve fit will be 0. Okay. Now when you go to 10 meter per second, when U is 10 meter per second, your Y is log of E minus A. So when U is 10 meter per second, if you go to the data here, your E is 3.99. For a velocity of 10 meters per second, E is given 3.99. So E is 3.99, A is 3.19. So logarithm of 3.99 minus 3.19 is minus 0.097. Similarly, when U is 10, log of 10 is 1, right? And you can also find that knowing the value of A, which is 3.19. Sorry, yeah. And if you know the value of U, sorry, this we will know after we find the fit. Okay, this is not trivial to know. We will come to this little after some time. But these two we have evaluated. These two only we need for the fitting. We need X, we need Y, right? So when U is 20, again there is a value of E from the table. When U is 20, it is 4.30. So corresponding to E 4.30, A is 3.19. You find log of E minus A is 0.045. And log of 20 is 1.301. Similarly, for 30, you get the value. Similarly, for 40, you get the values. So once you have X and Y, you can use this formula. See, Y equal to B plus MX. Okay. So this constant B is like in our whatever we learned in theory, it is like the A0. We said that Y equal to A0 plus A1X. So this A0 is given by this expression. This expression is there in your notes, whatever we have studied. Sum of xi into sum of xi yy minus sum of xi square, sum of yi divided by sum of xi whole square minus n into sum xi square. So now these values are already there. These are all xi's, these are all yi's, and you just substitute here. And if you find out, it will be minus 0.525. Okay. This is the capital B. And this capital B is nothing but log of small b. So this is basically log of small b. That means small b is 0.30. Okay. So you not only have the value of capital B, but you also have the value of small b. Then we get the value of M. So which is in our theory, whatever we have studied in the class, this is like A1. Okay. And the expression for A1 is sum of xi, sum of yi minus n into sum of xi yi divided by sum of xi square minus n into sum xi square. If you just substitute these xi's, yi's here, you get this as 0.43. Okay. And so if you know B, if you know M, you have the equation. That is, you get this as your log E plus A, okay, will be equal to, so that means log E minus 3.19 will be equal to minus 0.25 plus 0.43 into log U. So that relates U with U. Now, so this is the, this is, sorry, there is a mistake here. This should be 0.43 into x. Okay, this is correct. 0.43 into x. That is, x is basically your log U, and y is log E minus A. So this is correct. No problem. This is x, not multiplication. This is x. So this is basically the curve fit. Y equal to minus 0.525 plus 0.43x. Now this part we'll talk about now, but this is the fit we got from the above analysis. We are able to get B and M. So this is the equation we have gotten. Now this curve fit will have an error. Okay, what is the error? That error we need to find using the formula for standard error of fit. The standard error of fit is SYX, which is, this formula is also there. We studied in the class, which is the data point EI minus the value of E from the curve fit, from this curve fit, whole square divided by nu square root. And here in this case, the nu is the degree of freedom, which is number of data points minus M plus 1. Okay. And M is not the same. Okay, don't confuse this M and this M. This M is basically the degree of polynomial. So we are talking about a linear equation here, linear curve fit. So for M equal to 1. So 4 minus 1 plus 1 is 2. Okay. So the degree of freedom is 2. Nu is 2. And we have the value of EI in each case. So these are the values of EI. And from the fit, from this fit, if you substitute the value of U, you can read the value of ECI, right? The value of E from the curve fit is ECI. So it takes care of that sum. If you evaluate that, that is going to be 0.007. Now we are trying to find an, the best estimate of this curve fit. So we need to find T of nu with 95% probability. From the table, this gives you 4.30. And now if you take T 2,95 as the standard deviation error of fit divided by square root of n, it will give you 0.015. So the curve fit is basically going to be minus 0.525 plus 0.43x plus minus 0.015. So this probability you can take. Okay. If you take 90% probability, the value of T will change. Or if you take 99% probability, the value of T will change. But that is okay. For 95%, this will be the problem. Now, once you have this curve fit, you can then convert back to the form. That is, this form, E will be equal to 3.19 plus P is 0.3. So 0.3 U to the power M. And M you have found is 0.43. So this is basically the curve fit. Okay, 3.19 plus 0.3 U to the power 0.43. Okay, so this is how you will solve the second question.
Sir, one small doubt. Why can't we assume, because our requirement is to create an equation above 95% of the confidence interval.
Yeah.
Why can't we assume M and then proceed further? Because it might be, we were considering single order equation, and then even R square is found to be above 95. That's the reason why we thought of asking this question.
No.
In the given equation, rather than taking logs, and then if I assume M equal to 1 and then try to calculate the, if you, just correlate it to equal to
M equal to 1 will be a guess, right?
Because, it proceeds a guess,
But that is not, what we should be doing, because that may not give you the best fit. We are looking at the best fit, and the best fit is basically the fit that we get by minimizing the error through method of least square. Okay.
Okay.
If I ask you to do a linear fit, then it is okay. But we are asking you to find a best fit, so we have to basically follow the method of least square that we studied in the class. Okay, those are approximate methods. Okay.
Fine, sir. Yes. Thank you, sir.
Okay.
Sir, one more question, sir. Sir, the value of nu, how it is coming like 2, sir? Because 5 parameters are here, no, sir? 5 minus 2 will be...
So, if you look at here, when we are doing this curve fitting, we do not have value of, y and x. Even if we have a value of u, as I said, it is becoming log 0 and log 0. So, you do not have these values for u equal to 0. So, in fact, you actually used only 4 data points to evaluate, these parameters. Okay. So, that is why your n is actually 4, not 5. Okay.
Okay, sir.
Sir, there is a statement in the question regarding the goodness of fit.
So I have not done it here. So R square has a formula, right? Again, in terms of in terms of these xi,
minus
yi, and so
yx.
on. Okay. So I have not done that. I have skipped that inadvertently, but that will depend on xi and yi. So if you substitute these values, if you get r square greater than 0.9, then the fit will be considered to be good. Indeed, this syx and r square is related. So if when the standard error of fit is very small, it's sort of an indication that your r square will be greater than 0.9. Okay, you might have done this. I have not done it, but there is a formula that we have studied in the class, and it is going to only be a function of this xi and yi. So if you use the formula, you can get it. Okay. I am not able to find the lecture slide that we wrote for the curve fitting. That is why I am not able to project and show it to you. I was trying to find, but it is missing.
Sir, it's in one of the textbooks that you had shown, sir. 1 minus wyx by wy. I mean, or say sigma yx divided by sigma y.
Yeah.
And that's the formula, right? R square.
Yes.
So if
yeah, I had it in the class, but I don't have it in front of me. So, okay. So that is how you solve the second question. Now I will move on to the third question. So this is actually we had solved in the class a very similar question. Let me pull that out so that you will be able to recollect. I think it was somewhere here. Yeah. So we had solved this question that if you see that we are asking to find the mean and standard deviation, and we are asking you to find the interval and the best estimate of the mean. So you find mean by taking the sum xi over n, then sx as 1 over n minus 1, sum I equal to 1 to n, xi minus x mean square, whole square root. Then if you want to estimate the interval value over which 95% of the measurement would lie, then you have to find the t of nu p. Nu is basically the number of data points minus 1. In this case, we took 20, so this should be 19. P is 0.95. So if from the table, t distribution table, you can read this as 2.093. And the interval was mean plus minus t into the standard deviation. Okay, that is how you find the interval. And if you want to find the best estimate, you have to consider as the mean plus minus t, the standard deviation divided by square root of n. Okay. So this we had done in the class. And the question that I have asked you is exactly similar. So let us see how we do here. Similar method. Okay. So you find the true mean, which is sum of xi over n, and you get this as 8.2267. Then you find the standard deviation, which is 1 over n minus 1, sum of xi minus xm square, whole square root. Here n is 15. Okay. 15 data points are there. So that is how you find the true mean and standard deviation. The second bit is estimate the interval over which 95% of measurement will lie. So for that you need to get the t value. Okay. Here n is 15, and so the degree of freedom is 14, and it says 95% of value. So you have t 14.95. From the t table, you will read this as 2.14. So the interval will basically be t plus minus t 14.95 into the standard deviation, which is 2.14 into 1.6722. So the interval within which 95% of value data point should lie will be basically your 8.2267 plus minus 3.5785. Okay, this is basically the interval. Then the last bit is estimate the true mean value of X at 95% probability based on this finite data set. So for that, you have to find that it will be basically X mean plus minus T into Sx divided by square root of n, which will be 8.2267 plus minus. So this will be 2.14 into 1.6722 divided by square root of 15. That will give you 8.2267 plus minus 0.9240. So the true mean will lie within this range, 7.3 to 9.1. Okay. So this is again, I mean, something that we did in the class. So now I would move on to the last question, which is the fourth. It says the impulse response of a first order system is given by C as a function of time is 3 e to the power minus 0.5 t. You are asked to find time constant, DC gain, transfer function, and the step response if it were a step function. So let me show you this, this thing that we had covered when you have an impulse response. So impulse response is given by here, as here. And typically the transfer function has a form of k divided by ts plus 1, where k is the gain and t is the time constant. For an impulse response, your input is basically delta s is 1. So your output is basically k divided by ts plus 1. Okay. So CS you can write in also in this form. You can take outside. You can write it as k by t over s plus 1 over t. And so in the time domain, the response is going to be k by t e to the power minus t by t. So you have a equation given here which is in this form, right? This is the form. But it is asking you to find what is the time constant and what is the gain. Okay. So how do we do this question? So first we write Ct is 3 into e to the power minus 0.5 into t. So when you go to the frequency domain, as we saw here, the CS over Rs will be this transfer function k by ts plus 1, right? So CS over Rs is the transfer function k divided by ts plus 1. So here CS is basically 3 divided by s plus 0.5 into 1. Okay, so here like Ct is k by t e to the power minus t by t. So CS is k by t divided by s plus 1 over t. Right? This is something we had also seen here. Same thing. So when Ct is this, so your k by t is basically 3. Okay. And 1 over t is basically 0.5. So you have this in this form, k by t is 3, then s plus 1 over t is 0.5 into Rs is 1. Or you take it as delta s because it is an impulse function. So Cs divided by delta s or Cs divided by Rs, output divided by input in frequency domain, is basically 3 divided by s plus 0.5. So this is basically k by t. This is basically s plus 1 over t. So that means, so you can bring it to this form. Cs over Rs is 6 divided by 2s plus 1. Basically, it has taken to this form. K divided by 1 plus Ts. So clearly, your t is 2 seconds. Time constant is 2 seconds. K is the gain, which is 6. K is the DC gain. So the first two questions in this, first 2 points we have found. 2 seconds and this is 6. Now we find the transfer function. Transfer function is also found. This is basically the transfer function. K divided by Ts plus 1 is the transfer function. The next bit is the step response. So if this is the impulse response, what would be the step response? Okay, this is something that I have not shown it here. See, the step response is basically the integration of the impulse response. Okay, let me get that page. I have not shown. Give me a few seconds. So I hope you are able to see it. So this is basically the transfer function. Okay, Cs over Rs is 6 by 2s plus 1. And since the input now is a step input, so Rs is 1 over s, right? If you, this is how the step input is written. So the output will be 6 times 1 over s divided by 2s plus 1. And this you can write it as a by s plus b by 2s plus 1. Because why you write this way? Because you know the Laplace inverse of 1 over s, you know the Laplace inverse of 1 over 2s plus 1. So this can be written as 6 by s minus 6 by s plus 0.5. Okay, same thing. So if you take the Laplace inverse of this, that means you go from the frequency domain to the time domain. This will simply be 6. The Laplace inverse of 1 over s is basically 1. And Laplace inverse of 1 over 2s plus 1 is basically e to the power minus 0.5t. So this will be now the output, okay, of this step response. The same transfer function, but instead of an impulse function, you are giving a step function. So this will be the output. Alternatively, you can say that, this is my the response in the when I have an impulse function, when I have an impulse response. Now, how do I get a step response from an impulse response? We had discussed in the class that if you integrate an impulse response, you get a step response. So you can integrate. So when you integrate this, you get the corresponding step response. And if you integrate this right-hand side with time, you get minus 6 e to the power minus 0.5t plus some constant. Now, if you have the initial condition known, that means at t equal to 0, if the response is 0, that means the constant you can evaluate when t equal to 0, this is 1, so the constant is going to be 6. So the CST is basically 6 minus 6 into e to the power minus 0.5. So there are different ways you can do this. Okay. I hope this is clear to everybody. Any doubt you have?
Yes. Will we have marks for the steps are accurate? I'm sorry if that's a very.
Hello, can you speak louder?
Sorry, sir. Would there be marks for accurate steps or something like that? I'm sorry if that's a very.
Yeah. Well, I mean, see, okay, just
Recording stopped.
I will try to observe as much possible. We normally do step marking. Okay, so that means if you have approached the problem correctly and you have done some minor spelling mistake or minor calculation mistake, then we won't, completely cut the mark, right? For every step you do something wrong, only mark is deducted there. Okay, so that is what normally we do at IIT. We give step marking. Okay, so once I correct the papers, I can return to you, and you have a look, and if you think you deserve more mark, you get back to me. But normally the policy that I follow is that if you come for evaluation, if there is somewhere I should have cut mark and I have not cut, you should also be ready for that.
Sir, we cannot challenge your authority, sir. We are just requesting you to pass.
No, I know that. So because there may be somewhere I might have not deducted mark.
Sir, actually, what happened that question number 2
But
is.
don't worry about mark, etc. It's finally going to be a relative grading system. Okay, so that means as long as you are with the class, you are fine.
Professor, sir, one request I have is that basically on the day of exam there was a technical goof-up from code office, and that disturbed the whole sentiment and mood. So I request you to just I'm sorry to say this, but I'm just making a request to whatever possible you can do, sir. Please do it. It's a request, because question number 2 is really out of world, and we tried. I admit that I have just tried the log and all.
No, I also know that the question number 2 was difficult. In fact, if I would have given the same question to the regular students here, who are in touch with coursework, they also struggle. So I know that. Please do not think that, I am not aware of that. So, but the thing is, we always set the question thinking that, the students are excellent. We
Right.
cannot assume that,
Of course, sir.
students will not be able to solve. So, but don't worry about, grades, etc. As I said, in a relative grading system, if you are with the class, you are fine. Because, if the class is the topper is, let's say, whoever is scoring, whatever mark, that basically is 100, right?
Right.
Okay. So, I don't think really you need to worry too much about it. As a teacher, I know all these limitations and everything. I don't think you need to really. Okay. And if people are working and all that, so all those points are considered.
Thank you so much, sir.
Thank you, sir. Thank you so much, sir.
Thank you, sir. Thank you, sir.
Kind of, sir.
So,
kind of.
point, sorry for the interruption. I'm sorry, there is a network issues there, so I couldn't hear properly. On the last problem, if we draw the graph, then it is also right? Like the step response.
Yeah. If you draw the graph and you have indicated the values there, okay, because it is asking for values, right?
Yes, sir. Yeah.
So let's see. I have just started correcting, and once I finish everything, I will have maybe some generic suggestions to make. So,
Okay, sir. Okay, sure. Thank you, sir.
Thank you, sir.
So the answer sheet is shareable, sir. The one that you had presented now, is it shareable?
yeah, if you want, I can send it to you.
Yeah, sir. We
Sir,
would like to
additionally,
have
tomorrow
a.
do we have a class, sir?
Sorry,
Sorry, Keshav Prasad, I couldn't hear you. Sorry, I interrupted. I'll ask later.
I cannot hear you. What you said.
Sir, I interrupted one gentleman unknowingly. I'll just stop
Okay,
myself.
okay, fine. Okay, so if no further question, then we are not going to have class tomorrow. So we are meeting again Monday next week, right?
Sure, sir.
Okay, so have a good weekend. Happy Diwali to all of you.
Thank you, sir. Same to you, sir.
We meet
Shubha
tomorrow.
Deepavali, sir.
Thank you.
Thank you, sir.
Happy Diwali, sir.
Happy Deepavali.
Thank you.
Happy Diwali,
Same
sir.
to you.
Happy Diwali,
all of
sir.
you.
Bye.
Happy Diwali. Thank you, sir, and happy Diwali.
Thank you.
Yeah, thank you. Thank you all. Happy Diwali to everyone. Yeah. Bye.
Thank you all. Happy Diwali.